Я хочу открыть нашу сегодняшнюю лекцию и представить нашего докладчика. Меня зовут Алексей Гостомельский. Я управляющий директор Фонда инфраструктурных и образовательных программ Роснано. И сегодня в рамках открытого лектория мы проводим первую международную лекцию на тему гибкой электроники и ее влияние на будущее всего мира, какие применения она может предлагать. И ее проведет директор программы гибкой электроники Пол Херманс.
Thank you very much for the nice introduction. So, good morning everyone here. My name is Paul Hermans, and indeed I am going to talk to you about new forms of electronics. I realize this university is actually a university for steel and alloys, so it's maybe a little bit different. I will try to make maybe some analogies or some references to materials as much as I can. So, I have a few slides to explain where I come from. That's maybe also for students always interesting to know that. So, our company is called IMEC, and IMEC is actually a research institute. It's an R&D organization. And our headquarters is in Belgium. We tend to make a world map with Belgium in the middle. Basically, research center located in Belgium, as you can see on the map. We also have some side houses. One is in the Netherlands, quite close to our place, 100 kilometers north, called the Holt Center. We also have actually laboratories in China, in India, as well as in Taiwan. And we also have offices in Japan and in the United States. So what we do is actually research on microelectronics, or today this is called nanoelectronics. And basically the purpose, the goal of that is really to work on ICT, so that's information and communication technologies, on electronics for healthcare, and on electronics for power, such as electricity generation or also storage, as you will see in a minute. And we do that with industry directly, and that's our mission. So this is an aerial view of our facilities. You see there actually what we call clean rooms. So clean rooms are actually fab-like environments where we go actually from a mostly silicon wafer all the way to a silicon chip, and the technologies that you find between these steps. Now, we do that mostly on silicon, but we also have some other labs, and in the middle of the picture there you find what we call the thin film electronics lab, and as you will see, we are there innovating on other substrates than silicon. I will explain that in a minute. What I show on this graph is actually our population on researchers. So in total we are today about 2,300 people. And quite unique, I think, for the model of work that we do with our industrial partners is that about 1,500 of these, as you can see, are our own people, our own researchers, and about 500 of the researchers we have in our laboratories are actually sent by the companies with which we work. We call that open innovation in the sense that we invite the companies with which we work to send their own people to our labs, and that's a very efficient way to bring back the technologies to the companies themselves. We also work with PhD students, with many universities from the world actually. About 300 PhD students are working in our facilities and on our equipment. So it's a very international environment because of the nature of electronics. Innovation today does not happen in the boundaries of one country. Innovation, if you want to be a world leader in innovation, you do that with global players. You do that all over the planet, and the results you can see in this chart. We have in our laboratories 71 different nationalities working. So people from 71 different nationalities. And in fact, if you would zoom in, you would also find 14 people from Russia in our facilities. So I mentioned the topics are ICT, our health, and our power. So I represent these three application fields for electronics on this chart. And what I will be discussing mostly today is actually the Internet of Things application, which is a direct ICT application of electronics. In terms of technologies, we work on the left of this chart, yes, with silicon technology. Silicon is the substrate. Silicon is then also the semiconductor with which the transistors are made. But we also innovate on that. And on the right of this chart, you find flexible electronics. Flexible means the substrate is actually plastic. It's something mechanically pliable. And flexible electronics is the electronics that I will further discuss here today. So why do we use today plastic as a substrate? Well, plastic, you know the word plastic, refers actually to a mechanical property of a substrate of a material. Plastic means you can ply it, you can bend it. So it's actually shatterproof, it doesn't break like a ceramic material would. Silicon can be considered ceramic actually. It's also 2D bendable, and some researchers in the University of Tokyo have, for instance, demonstrated electronics that can work after it's being crumpled, really, like in the middle photograph here. It's also very lightweight, and lightweight also reduces, of course, the footprint, of the ecological footprint, because we have to transport a lot of goods, and weight is actually a very important factor in that. So these are some of the, I would say, mechanical properties associated to plastic. And we also use it because it also has unique properties when it comes to use. Use because we can integrate a thin plastic sheet more easily into all kinds of objects. So I show here in the bottom panel integration in textile. I show integration in rubber material of electronics, and you can think of integrating that therefore on body, where you need really something that stretches in 2 dimensions. We also show integration on paper, or actually in paper. We can make electronic fully disappear in an extremely thin sheet of paper. And so these integration properties means that we will be able to apply electronics in new ways. And on this chart, I show some of the ways that are coming up in the new technologies to come tomorrow. On the left upper corner, you find new displays. Displays that will no longer be on glass, but displays that will actually be bendable, flexible. Next to that, I show a runner. That's to demonstrate actually application on the skin to measure body parameters. For instance, temperature or sweat or other kinds of maybe heartbeat, or in a more elaborate future, even an electrocardiogram or something. Below that, I show a picture of X-rays, an X-ray imager, and that's on the bottom part at the right. Indeed, today we are working on making instruments, medical instruments, such as X-ray imagers, where actually the imager is made out of plastic as a substrate. It's lightweight, and the big advantage for doctors is that we could develop instruments where they can have a portable X-ray machine that they bring in their car to the patient, instead of the patient has to go to the hospital with a broken arm. So that's actually new things coming up also, making use of lightweight of this type of technologies. And on the bottom left there, I mention in general 3 letters, IoT. That is the abbreviation for Internet of Things. So we are making very small, lightweight plastic electronic chips that we will be able to integrate into everyday objects. And in this way, these objects will participate. They will be smart, they will have processing power on board, and they will participate in the Internet of everything. So you see, these are applications that become possible because of these new properties of electronics on plastic. I will now discuss a few of these. The first one here is the displays. I mentioned flexible displays are coming. In fact, the first displays that are fabricated on plastic as a substrate material, as opposed to glass as a substrate material, are already on the market. I show here two smartphones which were actually launched quite recently, last year, and where the display is on a plastic substrate. The display is not mechanically flexible yet. That is not possible in the state of the art, but it is already on plastic. So coming up next will of course then be displays which are truly mechanically flexible. And that is what we are today working on. And what I show in this slide, and the video will start, is actually developments that we did with Panasonic. And as you can see, this display, it's on plastic substrate, and you can actually bend it during operation. It's not yet a product. This is really our research with the companies today to actually develop this further such that it can become a product in the years to come. This was one example, and now the other part is for electronics, so not displays but electronics, as I mentioned. Today, what is flexible in electronics? Well, if you open a smartphone, you will see that there are printed circuit boards, as we call these. That's actually the board on which the chips are assembled. And they today already have flexible parts in there. And they do the flexible part because they fold up the printed circuit board into a very thin form factor for making the smartphone. So that's why today you find these curled up, foiled up printed circuit boards in smartphones of today. But the electronics, this is only the interconnect, which is foldable. But the electronics itself is not flexible at all. So what we will do now is coming, I would say, research, is to really bring also electronics where the circuits themselves become really flexible. And actually, if I'm here today in Russia, in Moscow, it is basically because we just have signed yesterday a contract with Artek Electronics, which is located in Troitsk, part of the Technospark there. And with that company, we will, as IMEC, innovate on flexible electronics for technology, as technology for the future. So basically, the goal will be to bring electronics to trillions of objects, to really many, many everyday objects. By analysts, it has been predicted that by the year 2020, more than 50 billion devices on the planet will be connected to internet. Really interconnected, electronically. And this is only the beginning. After the 50 billion that you see there, we expect hundreds of billions, trillions of objects interconnected with electronics. So this is really a shift of paradigm with respect to use of electronics today. Today, the amount of electronics surrounding us is proportional to the number of people using them. Every user has maybe 10 electronic devices on him. In the future, we no longer count the number of electronic devices by the number of people, but truly by the number of objects that we see around us. Because objects will be interconnected between one another, and that is what we need to realize. Now, when we look at the pervasion of electronics today, and I take here some living room, there is not so much electronics that you can find. In everyday objects, we don't see electronics. Electronics here is maybe limited to the television. However, when we look at the total amount of objects that surround us, we see that there are indeed objects of high value with a lot of electronics in there, such as cars, or such as the portable electronics that we have every day, the two top lines here on this graph. But when you look at all the other objects that surround us today, they are void of that electronics. There is no in garment, we don't find this in disposables and everyday objects. It's not present. And that is really the revolution that we will be able to perform with this new form of electronics. Now the question is first, do we need electronics on these everyday objects? Who is asking for this? What kind of economy would be associated to that? Well, first of all, if you look at the value that you could put in there, if we assume that just 1% of the value of all of those objects could be converted into electronic value for electronics, you arrive at staggering numbers. There is an opportunity there of multiple billion, hundreds of billions of, and I express here in dollars, you could express it in rubles, it would even be much higher. So there is a huge economic potential there. Still, it doesn't tell you whether it's really needed. So I now want to go to some application cases where we could use that. The first one I show here is retail. So the idea could be to give an electronic tag, an electronic label, to all the possible goods in a supermarket, in the shops. And why you would do that is because consumers today are very, very interested in knowing a lot of information of the goods, whether it contains allergens, where it comes from, when it was produced, how long it will stay fresh, and you can go on like that forever and ever. Now, of course, you cannot print all of that onto labels, and you would also have to change it continuously, because the product actually changes in lifetime as it is sitting in the shelf. So basically, the idea could be, we put an electronic tag on each and every item in the supermarket, and then by a smartphone, which is equipped with an NFC, which means near field communication electronic reader is present in every iPhone, you can actually read out all the information of that product by coming near to the label, the electronic label on the product. What then happens is that on the electronic label there is a unique identification code for this object. That unique identification code is read out by the smartphone. The smartphone is interconnected, is used as a hub to the internet, and all the information on that particular product was actually waiting for you in the cloud. And you can download it and read it on your smartphone just by looking at this object. So that's actually the idea behind this little picture. Similar, of course, you can imagine it can simplify and it can automatize a lot of processes in logistics. It can also give rise to a lot of new applications in logistics. And I show here as logistic example, actually luggage handling in airports. The first actually electronic tags for luggages exist. Of course, they are still quite expensive today. By going to our flexible electronics, we hope to make these affordable and actually pervasive. Another case could be actually integration in clothing. Today, and actually brand protection is of course important in that respect. It is analyzed again by analysts that about 5% of all the retail is counterfeit. That represents an enormous economic value. And in fact, you could recapture some of that value, and 5% of all the retail is a gigantic amount. You could recapture that if you could indeed equip every piece of authentic goods with an electronic label that actually not only identifies it as genuine, but it can also actually trace the origin and the production of the good from the place of production all the way to the hands of the consumer. Again, something that consumers of today, especially in the West, are quite concerned about. Now, these were just only identification examples. We can go a step further and not only do identification, but add to that sensors. I give here an example, actually, of a future. It's an imaginary picture. It doesn't exist today. Of a future product, which could be an electronic label, for instance, for food, where you would have the identification plus sensors and maybe some little display. Now, this label will tell you, for instance, okay, where does this meat come from? Who has produced it? Again, for the West, people are really concerned about this. Huh? At what temperature has it been kept since actually it was produced? Is it okay for consumption? Any pathological things on there, and so on. So you can actually really check the quality and the origin of that food in one glimpse. It could be simply displayed, as shown here, but again, also electronically transmitted to some smartphone. And then also, why not apply that to actually on the body? Yeah? You can imagine, for instance, disposable patches for all kinds of monitoring, your temperature, your heart rate, actually skincare monitoring. In the East, this is quite popular actually, to check color and tone of skin and match, for instance, makeup with specific properties of skin. So this is all examples where we think that indeed there is there is economic value in really going into making this type of electronics. But today it doesn't exist. And then you may wonder, why does it not exist? What is the difference between this electronics that I just now showed and the things that we can make today? If there is value in there, why was it not done before? Well, basically, let's have a look at the properties of electronics that would need to be given in order to be able to address kind of putting electronics on this kind of disposable goods. We would need electronics that we can make in trillions of amounts. And that's not so easy for silicon today. You need it to be disposable without leaving behind you an ecological footprint. So it has to be really kind of almost near zero amount of material left in there. You have to be able to integrate this electronics on these strange form factors like a box, a cardboard, paper, plastic, wrapping, and so on. And I asked for multiple functions. I asked for electronics, so these are transistors, as we translate that to transistors, but there was also sensors, and there were displays, and there were other things that I also need to add to this. So I need a platform, a technology platform, on which I can have all of these properties realized simultaneously. And what we have actually come to understand is that thin film technology, electronic technology, which we sometimes refer to as plastic electronics technology, is actually a suitable platform to at least start with this. So thin film will allow for all of these properties, and the reason I show here on the right now. First of all, the way we manufacture this. We don't manufacture this on silicon wafers, which are limited in size like that. But such kind of plastic electronics, the way we will manufacture it is actually similar to the displays. I showed the displays in the beginning. A television is actually a piece of electronics, but it's much, much larger than a silicon wafer and much, much larger than a chip. So a television is something really large. Today, they are made on glass. But as I say, tomorrow we are making these actually on plastic substrates. It's this type of electronic technology that we want to use for our transistors of this of our plastic electronics. So we call this flat panel display process compatible, compatible with the processes there, because this is produced in extremely large volumes at much lower cost structure than silicon fabs. The second is the form factor. The form factor, I mean with this plastic. Yeah, so plastic form factor, we directly produce this on very thin plastic sheet. To give you a number there, it's 25 micron. 25 micron is the thickness of your plastic household foil with which you wrap sandwiches. That's the thickness of our substrate. And the third is, indeed, integration of many types of devices. We have transistors on there, but as these technologies are used for displays, there is also a light emitting element on there, so a display element, and we can also integrate thin film sensors on there. And this way is the way we will go for this monolithic integration of all the functions. Of course, not everything is ready, but in the end, what I want to realize is indeed a very thin plastic sheet, 25 micron thick, with sensors, memory, logic, also battery. I did not much discuss that, but it's going to be important. I need some form of energy storage, displays, and wireless connectivity. So what I will now show in the next slides is basically, well, let me go back here, is basically where we are with some of these bullet points. What can we do today already? Because not everything is ready. And the first thing, I start from the bottom. I will go to that wireless connectivity. So basically, what we are working on is little tags, which we call near-field communication tags. This is actually creating the electronics whereby the little tag will be able to communicate wirelessly with a smartphone. Now, there is a certain protocol for that. You would like for many other things. The protocol we try to follow is the ISO 14443, just for your information. That is a standard protocol of communication that is developed today for near-field communication. And what we try to do is, with our plastic electronics, reach this milestone that we can communicate with this protocol. Because then we know that standard smartphones can actually connect with our tags. We're almost there, not fully, and we present our results very regularly at major design conferences. I mentioned here the conference ISSEC, which is actually the prime world design conference on which we usually are present with our latest scientific progress in this respect. So that's just wireless communication. For processing power, I like to show this example. This is also recent scientific work that we did, and it was published in the journal Nature, where we made actually a microprocessor on actually thin film technology. It's a microprocessor that is not working very, very fast yet today, but we are making progress there as well. And I have an example of such a microprocessor with me. So what you have here in this box, it's a plastic, fully transparent box, and you will find here a chip that we can have a look at it after my presentation maybe. So it's a transparent chip, if you wish, on very thin plastic foil, 25 micron thick, and this has the function of a full microprocessor. Other examples are sensors, because indeed we need sensors, and what you see here on this slide are some of our progress in the field of, again, flexible sensors. On the left, ion sensors. Think, for instance, you want to measure concentration of potassium chloride or something like that, which is proportional to your sweat on a runner. This could be one example. On the right, I show photodetectors. These are optical sensors that can detect the presence of light or even create full images. So you can see a shadow, or you can use this for all kinds of optical detections. Display segments are the other part. You remember the tag on the food, where you may want to have a direct display of what is going on that tag. So here we show an example of a flexible display element, and I have actually a video of that display element running. So the numbers in the center here, that's actually the little display. Those ones are the controller, so don't worry. And I call this a chipless counter. Why chipless? There is no silicon there to control the counter. There is simply no silicon. All of the control is again done by thin film transistors like these ones. No silicon on this thing. These are transistors. This does logic, but there is no silicon. It's all made on this thin film plastic technology. Same here for my counter. It's controlled by thin film electronics that you don't see. It's actually transparent in that counter. And then I mentioned solid-state battery. Yes, we also will need to make batteries. Today, most batteries are wet lithium-ion batteries. That's the ones you find in all of your electronics. And automatically it makes the battery actually quite bulky. If you open your smartphone, you will find a pouch in there, a pouch which is actually the real battery. It's fully encapsulated, very strongly protected, because it's highly flammable. If you break it open, if you let oxygen in, actually it's a bomb, because lithium in there will actually, the lithium electrolyte will actually explode. So we don't like this type of batteries, of course, on our thin plastic films. It's never going to work. So what we need to do is actually make new forms of batteries. What I show here is actually a state of the art, so just materials, two electrodes which contain a lot of lithium, and then a solid state electrolyte that can conduct lithium ions in between. That's how a normal battery is made. The problem with solid state battery today is that the amount of energy that you can store in there is very limited compared to the wet electrolyte batteries. And so that's precisely what we are now innovating by going through a three-dimensional structure for depositing the very thin films of the battery material. So we have novel technologies by which we deposit these materials on actually a three-dimensionally formed microstructure as substrate. And that gives a total amount of volume for this solid-state battery that will be competitive with wet batteries, but be solid. And that means you can integrate this as a thin film, and it's also safe for use. It will not explode. I now explained kind of the different pieces of the electronics that we are constructing as the days go by. Of course, with these pieces on a piece of plastic, it's not yet integrated into our objects. So there's still a need for a transformation process from the plastic sheet to the object. And that's the next piece where I will show some pictures of how we are doing that. First of all, here on this slide, I show the real reason why we chose plastic as a substrate. Plastic is very easy to work with. We can cut out plastic from a two-dimensional sheet. I can cut out a very special shape, which afterwards I can deform and, as you can see, create a three-dimensional object. So because it is plastic, and plastic is in the word, I can go from 2D to 3D. And that's precisely the transformation that you need to go to everyday objects. So if one example is shown here, we can then afterwards laminate this 2D cut out object into, for instance, textile. So this is close-up, an electron micrograph, actually showing the integration into textile or onto textile, actually with the light-emitting element here in the middle. And with this light-emitting element, then you can go to light-emitting textile, as shown here. So this is that integration. Another type of integration instead of lamination can be actually that you use the very thin piece of plastic and that you actually form the electronic part when it's a plastic part, for instance by injection molding on top of this plastic. And the plastic will deform, but it will keep its function. Okay? So what I show here is actually a thermomolded plastic say piece with on top of it, as you can see, electronic interconnects which have then been deformed because of that thermomolding process. But the electronic function would be present in that 3D shaped plastic. So that's the way that we are working on, say, the transformation. However, there is still one big issue left, and that is when you think of electronics, for instance, in textile. In textile, I need these electronics not to be just bendable in one dimension, but you really need it to be bendable in 2 dimensions, because you are crumpling your clothes when you wear them. And to go from, say, rigid to flex is one step. It's the step that we have now discussed on the plastic. However, how can we go from flex to 2-dimensionally flexible? Because in a 2-dimensional flexed thing, I always have areas which are really actually stretched and other ones which are compressed. And there are saddle points, there is mechanically very complicated profiles of strain going on there. So for that, we are working actually on a basic principle, which I show on this chart. Basically, we use little islands of plastic, flexible electronics, and we interconnect these with all the metal interconnects that are between the different islands of our electronics. Those we make kind of in a meandering shape. And this meandering shape is actually a spring. It's mechanically, this is a spring. So it's a spring that we make, of course, because for the making process, we make the spring in 2 dimensions, flat. We make it flat. But it allows for deformations in 3 dimensions because it's a spring. So the general principle we use is the electronics itself will be simply flexible, 1D, not very much therefore, but the interconnects between the electronics, that will actually be springy and therefore really elastically stretchable. I show an example of some piece of electronics that we have made like that. It's a display. So what you see here is actually a photograph of the display when you zoom into it. What you find there are the light-emitting pixels, are the different little pixels. They are not stretchable, they are kind of rigid. But in between these, you find actually springy interconnects, which actually provide all the electricity and all the signals to these light-emitting pixels. And they have been made in the shape of that spring. Okay, so that's the way we fabricate this. Then, actually, when you look at this, this is what it looks like when you zoom out a little bit. We then overmold that complete structure with a rubber material. When after you overmold it by rubber, this is what it looks like. And then, finally, we mount, of course, the display drivers. Today, we still mount these as rigid electronics at the side. But for future products, what we will do is we will cut up this electronics and distribute it all over the display. So that in the end, at the display, I will only have 2 wires or 3 wires coming in. 1 data, power, and ground. That's the future. But today, we still have this rigid electronics at the side. And in fact, here, you now see a video of this display as it is running. So it's, as you can see, really stretchable now, and it's also flexible in 2 dimensions because of the particular construction that we employed for it. And okay, that's the effect we have. And in fact, one of our customers has integrated this type of display already in clothing, in a textile, and you end up with actually a quite fancy, I would say, dress, for instance, where actually you can project really, I would say, still quite rudimentary in terms of resolution, but already really information on such a display. So this way we want to go to, say, textile integrated information displays in the future. Not there yet. So this actually was the last slide. It finishes my lecture. I thank you very much for your attention here today. And if you are interested in what IMEC is doing and the future of it, you can always follow us on our magazine, because we publish actually very regularly monthly a magazine, which is intended for the broader public to follow up on all kinds of innovations in electronics. So I can only recommend you to download it. It's also, of course, on mobile platforms such as smartphones. Thank you very much for your attention.
Have you already started to create the material which was showed in the last video?
So whether we have started to...
Are you mean in work right now, up on this material?
Absolutely, yes.
Absolutely. And in what time are you going to present it to, I mean, to social?
Well, today, yeah. So, in fact, what we here show, we need progress. We still need progress. It's an R&D. It's an R&D object. It's not something that you can today already use commercially, for 2 reasons. The first reason is that this display has actually still a little bit of low resolution. So in fact, I do mention the resolution there. It's 45 pixels by 80 pixels. When you compare that to a display, for instance, like your smartphone, it's actually too little, for instance, to show a video or to even show the normal information that you would like. It's very good already for what we would call signage. So if you want just to display a sign or a message, some people like to display messages on their t-shirts, you could change it, you could make it colorful, you could make it moving. So for signage, it will be okay. For information display, we still work on increasing the resolution. That's the first thing. The second thing, and it doesn't show so much in the video, is that we have to further improve the brightness. Because, in fact, it looks like obvious to make a display like that, but the truth is that you have to be very careful with heat dissipation and with current distribution across this complete display. It's really not obvious because it's so thin. It's just wires in a stretchable matrix. And to do that, we are moving now from, for technical people, a passive matrix display to an active matrix concept, where we will be able to actually improve much on the brightness and avoid peak brightnesses. But that part is not ready yet. What I show here is our first generation, which is the passive matrix. By doing it, we know what we need now, a second step. And the third problem we have at this moment, and why it's not commercial yet, is that the cost would be way too high. If we had to make that for you, the cost would be prohibitive. And the reason why the cost is prohibitive is because to make this first appealing demonstration, we have not been able to fully use thin film technology. Mainly, all of these light points are individual LEDs, little light emitting diodes, which were assembled by pick and place on this substrate. So if now you can imagine that I don't do this for 45 by 80 LEDs, but I do that tomorrow for 450 by 800 LEDs, you can imagine how many pick and place operations this will not work. So we need to find a new method of fabrication, or we have to move this from these LEDs to a thin film technology. So for these reasons, we are working on that technology to indeed make it something that tomorrow you can use in a product, but it is not ready yet. It is a demonstration of what is coming up. It's like science fiction.
Okay, it's kind of concept right now, yes?
It's a concept.
Thank you.
Yeah. But you see, we show these kind of examples as R&D, and then when people pick it up, we develop it, and we know exactly what the points are that need to be worked on. Technologically, it's all feasible. It's a matter of doing it.
Подскажите, пожалуйста, что повлияло на ваше решение связать свою жизнь с новыми материалами?
Well, that's indeed a more personal question. So basically, I am by training an electric engineer. That's my training. An engineer, electrical engineering. And basically, during my researcher career, I switched subjects, I would say, gradually. Starting with silicon, going over to optoelectronics. These are electronic devices that emit light. And then some 15 years ago, you know, the new forms of electronics were coming up, which were plastic and flexible. Of course, for a researcher, that is fascinating. You know that this is the future. So, in IMEC, we have the opportunity to change and switch, propose new ideas, and innovate on that. But the decision is yours, and the responsibility is yours. So, in other words, you have the opportunity to innovate, take it, and take the risk, and simply make sure that you are. The work you do is relevant for the world and for the industry. That's it's, in other words, a path that is completely, I would say, evolutionary, starting from a basic background in physics and engineering.
Hello again. I want to ask, as I understood, this film, you store only information in there and then you can carry it anywhere. Am I right? And is there any ways to get rid of all these batteries and processors and just modificate information on the surface itself?
Yeah, in fact, it's a good question. So basically, if you wish, you might say that, when I look at a barcode is actually simply a coding with a print on the surface itself which carries the information. So barcode is actually what you propose, namely you put information on the surface itself. Right? In fact, we have that. That's where we come from. That's what we had.
Yeah.
And we want now to, because of course the amount of information that you can put there is quite limited. You can also not change that because it's printed, so that's it. Of course, if I just make an identification code, so I cannot make with a barcode an identification for 1 trillion different objects. That's not possible because my resolution of my print will not allow that. So, if I take just 128 bit, so 128 times 0 and 1. This is, for electronics, a very small memory, 128 bit. It's kind of nothing. Now you calculate 2 to the power 128. You will be amazed what number you get. 2 to the power 128. These are more possible objects than every leaf on the trees on Earth, right?
Right, yeah.
So that is the difference when you go from printing it on a surface and going for a little electronic tag where you use Boolean algebra to code for these same objects. And in addition, they will be able to display it on the mount, to maybe modify the memory, because we are working on reprogrammable memory, also in the same forms, and to add sensors. And that is really the difference. Okay?
Thanks for answering.
Thank you very much. It's actually a very good question.
Какую роль вы отводите российской науке в области новых материалов?
Okay, so in general, I would say, first of all, of course, Russia is very famous, was very famous for its scientists in general. I think that's a fact, and we all know that, and we are, born with this knowledge. So that's a fact. And quite clearly, what is also very much present here in Russia in general are kind of the raw materials. Now, how you transform raw materials to materials all the way that I can use in electronics, of course, I'm not there to give you a roadmap for that. But that is kind of chemical industry, which I'm sure is present as well, that is needed for that. So the only message I can give you is that yes, we still need new materials, a lot of them, for many, many of the things which I said. So there are opportunities there. And I'm not there to dictate what opportunities Russia has to take, but I can only, for everyone who is interested, point to some of these opportunities. And it's up to you to take the initiative to actually get it done.
So I have kind of personal question. And what kind of device would you like to have on your own based on these technologies? Because I can't see many applications to this, to be honest.
Well, the devices that I think will help my personal life in this, definitely I start with actually a better, starting from the very beginning of my talk, a better display. Clearly, when I drop this display, it's still broken. And second, I have a huge problem in this display because it's too small. So I want actually a device which I can carry, which is small, and that then I unfold to read actually a big display. So I want, certainly, as first one, a big display that I can carry in a small, that I can fold back and carry in a small form factor when I don't need it. There is no doubt that this is number one. Then, apart from this, I don't necessarily want any of the devices for the Internet of Things which I showed. I want applications that are built on these devices. In other words, I want the electronics in my daily environment to be there to help me to make decisions if needed, even in my place, But I don't want to be constantly pushing buttons and fighting with software to get this done. So this electronics has to really disappear in my environment and help my life without me even worrying about this. And that is precisely why I don't, I would say, want any device, but I want this technology because of the applications that will simplify my life.
Yeah. In this presentation, you told about flexible displays. For example, I understand that like this display may be stretchable in 2 dimensions. But if it tells about, for example, displays which may be stretched from 5" to 7". Do some researchers conduct in these ways?
Yes. Regarding, so in terms, if we go back to displays, I discussed actually several types of them. One I just now mentioned is one that I would just flex, for instance, fold over, like a newspaper. That could be one. The second one I discussed was indeed slightly stretchable enough such that when I integrate it on textile, it works, it doesn't break. And for that you need to be able to flex it in 2 dimensions. But the amount of stretch that you apply is not more than a few percent. It's maybe 5%, that's enough. Because my textile, I can also not stretch it more than 5%. So more than that is not needed. Now there are, and we also have some research on completely different form factors of displays which you refer to. Namely, making a display which is a standard size, maybe like this, and then be able to glue it on the wall while stretching it, such that at the end of the day I can make a display which looks like this, or bigger or smaller. No, actually smaller will never work, but actually adapt the form to, for instance, a screen that you have in a certain place. And indeed, we even have a Belgian company called Barco, who is actually also thinking about whether we could make this type of displays where you start with a specific size and you stretch it in 1 or 2 dimensions up to maybe 100%, so double the size, to fit a different form factor. It could be made with similar technology. And the difference is that the springs, I will go back maybe to the presentation. So I'm not sure, well actually I will go back to this one. So if this is, there we are. If this is a light emitting element of the display and this is one and this is one, then we could think of such display if the spring, which has all the interconnects, can be kind of elongated by factor 2 maybe, and it needs to be actually elongated only one time, because I would have the display, for instance, stretched in this direction and then fix it like this. So we are indeed thinking of using exactly this same principle to make displays that you could actually change quite significantly in form, like maybe 20%. But because of the property of the metal, you can imagine this will be then kind of a one-time, because we would actually no longer go in the elastic regime of the strain, but you would probably move to the what is that called, the plastic regime of the strain, where you actually keep the strain permanent, or the shape permanently deformed. That's the difference. By using the metal springs and go to the plastic deformation regime instead of staying in the elastic deformation regime.
Is the bending line a concern for you now when you're talking about folding materials?
I understand your question. So indeed, we go back to the foldable display, for instance, where you will have one place in the display where actually very often, very repetitively, maybe 10,000 times over the lifetime, you will fold it back and forth. So we, of course, have to consider all the mechanics, in fact, all the mechanical properties of the complete material stack that sits in that folding line. First of all, we have to consider what bending radius are we talking about. For a display, we believe that the bending radius could be, for instance, 1 millimeter, because the total thickness of the display will be less than half a millimeter, and then a 1 millimeter bending radius with 2 half millimeter planes means a 2 millimeter display only. So very thin still, and that you can open. Now when you consider 1 millimeter bending radius, for instance, what we have to look at is now translate that into what strain is there, so what amount of elongation or compression do you ask. Of course, it depends on the thickness, because this is all mechanics. It depends on the thickness of what we are constructing. So, guess what? We put the electronics, everything, in the neutral plane as much as we can. So very close to the neutral plane of that construction. And we also know kind of the rule that none of the materials that we want to put in there will actually tolerate repetitive strain above of the order of 1, maybe 1.5%. So we know we have design rules for what is the maximum mechanical strain that we can tolerate for repetitive bending with a security margin, and that's typically 1%. So it all boils down to a mechanical design of the stack at the particular place of the bending. And okay, that's why we use extremely thin layers of everything, like the real flexible layers, the total thickness of that will ultimately be probably only 20 micron thick, and the rest will be more rubbery material. The rest of the half millimeter thick display will be more really stretchable rubber material. But the complete electronic part has to be limited to probably 20 micron. And when you think of a 20 micron thick film and you bend it over 1/2 millimeter, the strain is not excessive, although it looks spectacular when you fold it. It's all mechanical design that comes on top, of course, of electronic design.
Hello, Paul.
Yes.
My name is Artyom. I'm sorry I'm a bit late. Have you said about yourself, about your life, about interesting facts?
Interesting facts?
If no, can you tell us about it?
I'm not sure I have an interesting life. So as I already mentioned, I'm an electrical engineer by training. So I was born in Belgium. The language we speak there is Dutch, for the part of Belgium where I live in, but there is also French. And because it's such a small country, I think most of us speak English as well. So my Russian is 0, if you want to know. So I'm an electrical engineer by training, apart from this. I'm married, I have 3 children, and they are, I guess, about your age for my elder son. He's 22. Okay, fine. And as I said, I have a career in research. I started actually with a PhD. I went on as a kind of a professional researcher in IMEC. In parallel, I'm actually also a part-time professor at the University of Leuven, because IMEC is located in Leuven. It's a university town. So we have actually the biggest university of Belgium. It's about 40,000 students in total. All the faculties are there. I'm in electrical engineering, a professor. And the University of Leuven was actually founded in 1425. So it's one of the old universities of Europe, together with Bologna and Heidelberg and Cambridge. Leuven was amongst the first universities to be created in Europe. I have no merit at all in that, as you can imagine. But okay, so yeah, I think it's really fun to, on the one, to have actually a combination where on the one side you can teach, and on the other side you can always stay at the forefront of the new kind of technologies. We always think of technologies that are still 5 to sometimes even 10 years from the marketplace. And it's on the one side, of course, a big challenge. On the other side, it's a fantastic opportunity and really a career I can advise to everyone, because it's personally extremely satisfying. Thank you for the question.
So, Mr. Hermansen, Thank you very much for giving your lecture. And finally, let us, behalf on Nas Mrs., congratulate you with your birthday.
Thank you very much. It's for having thought of this. Yeah. Thank you. You get 3 kisses from me? No? And thank you very much for the very nice flowers. So thank you for this.